The first thing that I would like to address is I would like to talk about another example. This is more realistic than the artificial potential energies that we used so far, and that's called quantum harmonic oscillator. Well, we're doing quantum, right? But harmonic oscillator. Now, if I ask you what's a harmonic oscillator, you will tell me it's this. And your immediate thought is, well, why the bleep would I care, and why do I care about quantum? Like, why do I care about this thing? Okay, I'm an electrical engineer. I'm not interested in masses on springs. Well, let's see. So what's the potential energy of this thing? Well, it looks something like this, right? So potential energy is a function of position. It looks something like that. Can you think of another example where there's a parabolic potential energy, right? So U equals 1/2 kx squared. Can you sort of open your mind and think of another example where you would encounter this kind of potential energy function, i.e., where you would encounter an example of a linear restoring force, right? So this, remember, potential energy and conservative forces are equivalent, right? So this is F, restoring force, and it looks like this, right? So this says that when a particle is on the right, there's a force pointing to the left, negative. When a particle is on the left of the neutral point, there's a force pointing to the right, positive. Okay, so these things are equivalent. The two pictures are equivalent. We're dealing with U because Schrödinger's equation is based on U, right? So where else might you encounter something like this? Well, what if I have two masses on springs, right? So I have, let's say, two different masses, M and M, and with this spring potential energy. Well, without hiding things under the rug, it's basically the same problem. You haven't seen it in this form. In the introductory physics, it's always a mass attached to the wall, but it's basically the same thing. Turns out you can change coordinates so that this is an effective mass. It's called reduced mass. The details are unimportant. It's basically the same problem. Okay, and then you stare at this dumbbell looking thing. You say, wait a second. Where else do I encounter dumbbells? Where else do I encounter dumbbells? Masses on springs? No, I don't know. It's not real. Okay, so let me stop this sharing. I'm going to share something else. Okay, you have to understand that lots of things experience a linear restoring force. Spring is just a physical model of a linear restoring force, i.e., it's just a model of a parabolic potential energy. What else can exhibit a linear restoring force? And the answer is almost everything. Okay? Let's say you're angry with this course, and deep down you may be like fantasizing about like ripping this professor apart. Okay, let's stick with that, right? So imagine one person grabs me by the arms, the other person grabs me by the legs, and you start pulling on me, right? Okay. Well, guess what? You will experience a linear restoring force. My body will apply a linear restoring force. Unless you pull too hard, okay, then it's not a linear restoring force. But at sufficiently small extensions, my body acts like a spring. Now, I don't have a shape of a spring, but it will apply a linear restoring force. You take an eraser, like one of those parallelepiped erasers. When you squeeze it or stretch it, for sufficiently small squeeze, a sufficiently large stretch, it applies a linear restoring force. You take almost anything that's squishy or stretchy, for sufficiently small squish or stretch, it applies a linear restoring force. I dare you to find examples that do not apply linear restoring force. And you may say, well, fine, but why quantum? I don't care about quantizing my eraser or quantizing my professor. Well, like I said, lots of things apply linear restoring force, i.e. obey parabolic potential energies. So now I'm gonna follow with my promise. I'm going to share the screen with something else. Okay, so let me, okay, so here's a simulation of a diatomic molecule. Okay, so you probably don't see the, you probably cannot see the iPad anymore, and that's fine. Okay, so let me reset. Okay, so let me choose argon. Okay, so first of all, what is the potential energy? What does this potential energy tell us? Minus the derivative, boom, gives a force immediately. In your mind's eye, take a minus the derivative. Okay, so the derivative here is positive, so the force is negative. In other words, if I pull this atom and I let go, it will be attracted here, right? What if I compress it, right? So the left atom is held fixed just for simplicity, okay? What if I now compress, I force one atom to the other? No, they don't like it. So there's some kind of an interaction, some kind of an interaction force that will push this atom away, okay? And as advertised, if, so here's a case where initially you have zero kinetic energy, but you have potential energy such that the total energy is above the value of the potential energy at infinity. So if I let go, would this be a scattering state or bound state? It would be a scattering state. See, the atom never returns. On the other hand, if I push it just a little bit, would this be a scattering state or a bound state? It's a class. I'm asking this question in the classical context. It's oscillating between the turning points. Now, this is a model of an interaction potential energy between the two atoms. Here you have force that's pushing it towards the equilibrium point, and here you have a force that's pushing it towards the equilibrium point. And if you don't pull it too much or don't push it too much, it will oscillate around the equilibrium distance between the atoms. Well, guess what? Is this a harmonic oscillator? No, it's not a harmonic oscillator. Why? Because it's not a parabolic potential energy. But if I, how do I stop this thing? If I take the atom here and I give it energy that's just a little bit of the minimum, it will oscillate around that minimum, right? The two turning points are very close. And if you zoom in here, it's approximately parabolic. And the closer you are to the equilibrium point, the better that parabolic approximation is. Okay, so let's try. So I can adjust this, and I can adjust this, okay? And I can accentuate this parabolic effect. So here is an atom that's vibrating around the equilibrium point. There isn't a coil spring between them, but the potential energy between them is approximately parabolic, close to equilibrium. Granted, if you really yank this thing like that, it will not be described by the parabolic potential energy. But if you, how do I return it back? But if you excite this molecule, this diatomic molecule, not too much, if you don't disturb it too much, it's described by harmonic oscillator, okay? So this is kind of an advertisement, like, why do we care? Well, we care because almost everything is a harmonic oscillator, okay? All of your molecular physics inevitably involves harmonic oscillators. You might say, well, okay, fine, I don't do molecular physics, I'm an electrical engineer. Well, fine, okay, so then think of this as just another example of a quantum bound state, okay? Okay, so now I'm gonna return back, and I'm, to your delight, I'm not going to solve this problem because it's just too difficult to solve. I will just give you exactly what you want. I will just give you the quote unquote formula. Okay, I'll just give you the answer. Okay, so let me, I'm gonna have to pause. And I'm gonna have to, folks, I'm sorry, I'm gonna have to, let's see. I will be back. Okay, now I promised I will not derive anything today, not very much. I never derive anything, okay? I solve problems, but fine. We have a different definition of what solving problems means, so fine. I'll stick to your definition today, but I will set it up, okay? So Schrodinger's equation, the time-independent Schrodinger's equation, right? So we already separated the time part from the spatial part. So the time-independent Schrodinger's equation for the little psi reads minus h bar squared over 2m d squared psi dx squared plus 1/2. I will use, you know what, let me use script kappa for spring constant, right? So this is spring constant because we use k often for like wave number. Okay. So this is what a time-independent Schrodinger's equation looks like. And I'm going to define, again, kind of on a foresight, omega naught, wink, wink, angular frequency reference. Okay. So with this definition, I rewrite my problem like this: minus h bar squared over 2m plus 1/2 m omega naught squared x squared psi equals e psi. Okay. And I'm using omega naught to avoid confusion with omega. Okay, so not to be confused with omega, which is equal to root e over h bar, as always, right? So that's why I'm using a different letter. Look, long story short, can you, oh, sorry. Like if I gave you something like that, would you be able to solve an equation, like differential equation like this? If I gave you 3 psi double prime, second derivative, plus 4 psi equals 7 psi. 4 times x squared. Find psi of x. Actually, let me make it even a more familiar notation for you. So this equation has this form. It has this form of 3y double prime plus 4x squared times y equals 7y, and I want y of x. This is not ordinary differential equation with constant coefficients, right? So not constant coefficients. So the general solution is not a sum of sines, cosines, or exponentials. It's because of this gadget right here. Those of you who took linear analysis probably remember something called a series solution, like way, way back, right? That's something that's been long forgotten and is a distant memory, and the final has already taken place, right? So why remember? But you might remember something called series solution. So the way you would solve an equation like this, this is a constant, this is a constant, this is a constant. So it's basically of the same form, is using a series method. And that solution again, it's a second order differential equation, so there will be two undefined coefficients in it. Long story short is that solution is a sum of two general solutions, one of which goes to infinity at x equals plus and minus infinity. And that violates normalizability. So the boundary conditions here are normalizability. So we want we want this kind of thing. Equals 1. And so that means we can't have bits that go to infinity at x equals plus and minus infinity. And so it turns out that this is only possible for discrete values of E. So again, we see that the quantization is enforced by boundary conditions. Okay, so now I will just state the answer is, a long story short. Okay, so this is only possible for discrete values of E. And these are E sub n. N is a counter, first level, second level, and so on. N plus 1/2 h bar times omega naught. Now, n here is allowed to be 0, 1, 2, 3. So E sub 0, the ground state energy, equals 1/2 h bar omega naught. Okay, so this is actually very interesting. This is very interesting because it shows us that in contrast to classical physics, you cannot have a zero energy. We've already seen that in particle in the box and a particle in a finite well. If you notice, the ground state energy is always non-zero. So imagine like your mass on a spring. Can you have the mass on a spring have zero energy? Classically, yes. You just place the mass at the bottom of the potential well or the equilibrium point, and it's resting there. So it has no kinetic energy, and potential energy is 0. So it has energy 0. Quantum mechanics says, well, you cannot have a zero energy. The harmonic oscillator always jiggles around. This is very interesting. If you think about it, this is a consequence of the uncertainty principle. We cannot have the zero energy scenario in quantum mechanics like we do in classical mechanics, because in classical mechanics, zero energy means both the position is defined, 0, or equilibrium point, well defined, and the momentum is also 0. In classical mechanics, that's fine, okay? But quantum mechanics, well, if position is well defined, the momentum is not defined at all. So the momentum, you cannot say that momentum is 0, right? So you have a very large spread of measured momentum. And so you will have a very large spread of measured kinetic energies. And so when you take the average of those, you will not get a 0, okay? On the other hand, if you know the momentum to be 0, well, then you have a very large spread in position. So when you do measure the position, you're gonna find the harmonic oscillator all over the x-axis. So in all of these measurements, some of them will be extended far from the equilibrium, some a little bit to the left, but the average potential energy will be non-zero, because the potential energy goes like x squared. So even though the average position will be 0, but the average potential energy will be non-zero. And so again, when you average all the energies, you will come up with a non-zero answer. So this is very interesting. The fact, fundamentally, the fact that you cannot have a truly a 0 ground state energy is rooted in the uncertainty principle. in the Heisenberg uncertainty principle. And the consequences are very far reaching. So I'm just gonna go and tell you a little fairy tale just for a few minutes. If we look at something like electromagnetic field, so on the side, what's the energy? So if I have a volume of space, okay, let's say I have electric and magnetic field, some cube of some volume, like your room. Okay, so EM energy density, energy per volume, is proportional to a constant times E squared plus some other constant times B squared. This is electric field, and this is magnetic field. Now these A and B, they're proportional to epsilon naught, mu naught, those constants of E and M. The point is, it almost looks like the energy of a harmonic oscillator. For harmonic oscillator, it's 1/2 p squared over m plus 1/2 kx squared. Okay, so you have p squared and x squared. Here we have E squared and B squared. So this is energy density. And so the energy in a volume, well, it's something like, well, it's really the integral of this over volume, but if E and B are constant, then it's just basically, you know, E squared plus B squared times the volume. So in a finite volume of space, there's a finite energy stored in fields, okay? Energy is stored in fields. So for example, if you have a capacitor and between the capacitor you have a uniform field, the energy, when you charge the capacitor, you stored potential energy in the capacitor. Where's that energy stored? It's stored in the field, in the electric field between the plates of the capacitor. And my point is, well, the energy, or energy density, stored in electromagnetic fields, it's a sum of something like E squared plus B squared, and it looks like a harmonic oscillator. And so it will not take too much imagination with this setup. It will not take too much of your imagination to conclude that you can never have such a thing as true vacuum. You can have a vacuum maybe without particles, but you cannot have a vacuum with no fields. That is a really startling conclusion, but you see, it doesn't require you to take very advanced physics because, well, this looks like harmonic oscillator, and we just saw that harmonic oscillator cannot have a truly zero energy. And so you conclude that no such thing as a vacuum with no EM fields. That is really a tantalizing quantum mechanical prediction, which really comes from this idea that the ground state energy cannot truly be zero because of the uncertainty principle. So imagine you're in deep space, in some intergalactic, deep space. It's not really vacuum. There are electromagnetic fields in there. And not only that, every once in a while, those fields will experience a spontaneous fluctuation to a more excited state. And that fluctuation can be realized in the appearance of particles that pop out of the vacuum for a brief instant of time, and then they annihilate each other. So there's no such thing as vacuum. And not only there's no such thing as vacuum, because of these fluctuations that are again related to the uncertainty principle, every once in a while, the fields will experience an excitation. And an excitation of a field is actually equivalent to a particle. Particle is an excitation of a field. And so what that means is every once in a while, you get spontaneous appearance of something like electron-positron pair, and they recombine and annihilate each other. Anyway, so I thought this was kind of a fun detour. You might say, well, I'm an electrical engineer. I don't care about this particles. Well, okay, fine. But I think this is, we're staring at the face of something very important. That's what I'm trying to say. Anyway, so back to harmonic oscillator. back to harmonic oscillator. What about the wave functions? What about the wave functions? Well, the wave functions, there's some functions. They're not easy, right? So I will just give you an example. The zeroth wave function. What about size? The zeroth order wave function is given by the following thing. And I might use slightly different notation than your textbook. Sorry, this is a quarter. 1 over, so this is 1, so this is going to be 1. For the first wave function, is going to be 1. Let me just do this. So this is a ground state wave function times e to the minus a squared x squared over 2, where a, so it's some kind of a characteristic width of this Gaussian is given by m omega naught over h bar. This looks like a lot of constants, and I agree. And it's basically a Gaussian, right? It's already pre-normalized. And it looks like it's a Gaussian. It's a Gaussian function. What about the first excited state? So this is ground state wave function. And we can immediately see from here, well, the most likely place to find a harmonic oscillator at the ground state is at the equilibrium point. That's true. But every once in a while, you will find it away from the equilibrium point, right? That's what's costing that ground state energy. Okay, so sometimes it will be found away, but it has, you can talk about full width at half maximum that goes like something like A, okay? So full width at half maximum is proportional to, it's proportional to 1 over A. So the larger the A, the more localized this wave function is. In other words, the larger is the spring constant, so the larger is the omega naught, the larger is A, and then it's more and more localized around the equilibrium point. On the other hand, the softer the spring is, the smaller the spring constant, the smaller is the omega naught. And so the more gradual is the decay of this thing, right? So this is kind of like, it's going to be something like this. So this is larger A, and this is smaller A. Okay. Okay, the average position, you don't have to do any calculation. You can find that the average is going to be 0. You could find standard deviation, for example. Maybe there will be a homework exercise when you actually do that. And it will be something like 1 over 8. It's going to be proportional to 1 over 8, right? So, and so you can see that the standard deviation is going to be proportional to 1 over 8. Okay, well, let me give you a first excited state wave function, and then I will show you some graphs. It's going to be, again, m omega naught over pi h bar, and you don't have to memorize that, right? So if I ask you to do some calculations for practice, of course, I will give them to you. 1 over the square root of 2 times 2x times e to the minus a squared x squared over 2. And this one will look, it's an odd function, right? Because you see odd times even is odd. And this wave function, now it's wave function I'm drawing, not the wave function squared. It looks kind of like this. Okay, so this is psi 1, and so on and so on. Now I want to share the screen with you. I want to show you a few of these, a few low-lying wave functions. So here are the first few wave functions: psi 1, psi 2, psi 0, psi 1, psi 2, psi 3. The number of nodes increases, the number of wiggles increases, and so So I just wrote down the functional form for the first two, and I showed you the graph. So now let me share with you the 100th wave function. So this is the 100th wave function squared. So this is what the probability density and the 100th mode looks like. It's a fairly highly excited thing. And you can see that there's kind of a shape. There are wiggles, but then there is an overall shape. And if we look at higher and higher and higher excited states, we will see again something that we already saw with the particle in the box. The number of wiggles increases. And when you look at the average of that, you're going to get this dashed line. Hopefully you can see the dashed curve. And the dashed curve is a classical probability density. What do I mean by classical probability density? Well, it means if you have an ensemble of classical harmonic oscillators and you all start with different initial conditions, then you randomly catch one, you're more likely to catch it at the ends, because that's where the harmonic oscillator slows down. So it spends more time near turning points, and it zips by really quickly through the equilibrium position. That's why the probability is a little bit lower there. And so again, we kind of see the inkling that we recover some kind of classical behavior in a highly excited state. And also, I guess I should say that also, when we look at the energies, notice that in contrast to the particle in the box, here all the energy spacings are the same. So if you look at the formula for the energy, 1/2 h bar omega, you can see that, so here's the energy axis, here's the ground state energy, so here's your 0. The ground state 1/2 h bar omega, and you can see that all the energies are equally spaced, E1, E2, E3, and the delta energy between any level is actually h bar omega, right? So you can just see this. You can do En plus 1 minus En, and they're all separated by h bar omega. And so again, we see that delta E divided by E is proportional to 1/n, which goes to 0. So when you look at a if you look at large energy, right, all these energy spacings look very close together. So it's almost like a continuum energy spectrum, which is what you get in a classical harmonic oscillator. Classical harmonic oscillator can vibrate with any energy you want, depending on how much energy you gave it from the start. And we kind of recover that again. Okay, so that's the harmonic oscillator example. See you.